You did it? I just shifted the quiz for the rest of the class. Is that okay with you?
Yeah.
Good. I mean, you don't feel like you are under disadvantage or anything like that. Good. Are there any questions from the homework? Yes.
Number 12.
Number 12. From which section?
5.2.
5.2. What's that? Number 12. Just take log. That's it. Yeah, so number 12 says what? AK is AK minus 1 times AK minus 2. And then A0 is 1 and A1 is 2. Okay? Then what do? Take BK to be ln of AK. They're all positive, so that's all defined. So what you have then? You have what? BK equals BK minus 1 plus BK minus 2. And that's Fibonacci sequence where what? B0 is 0 and B1 is ln2. So here it is. So Bn is Fibonacci sequence with those conditions, and then AK is just e to the bk. That's it. What else? Yeah. What might be better? It might be better to actually, instead of ln, to do log. And then this would be what? 10 to the bk. And that's it. So bk is Fibonacci sequence with the starting values b0 and b1, and then when you get that Fibonacci, so if you have a program for Fibonacci sequence, then you can write this one. So AK is 10 to the bk. By the way, I will give you a formula for Fibonacci sequence today. We didn't see that formula. We just saw the limit last time. But today we'll see Fibonacci. So B2 is what? Also log 2. And then how is this related to the Fibonacci sequence? B1, original Fibonacci sequence starts with 1, 1. Do you agree? So generally you can say what? That BK is log 2 times Fibonacci sequence for k. And then AK is 10 to the log 2 times Fibonacci sequence for k. So that's the answer. Next question. If not, then let's start section 5.3. 5.3 is more similar to section 5.2. I hope you felt the difference. In section 5.2, you are actually doing word problems. You need to design procedure that connects new member with the old members, and that just changes from one problem to another. Then in section 5.2, we wanted to recognize some most famous and most typical recursive configurations like arithmetic and geometric sequence, so that when you deal with them, you don't kind of set up things and go forever, but just you call the formulas because there are summation formulas. Today in section 5.3, we'll do a recurrence relations where we can do something similar, and I announced that last time that our topic for today is quite in line with something that you studied or you will study in your differential equations course. So actually I will skip the beginning part of it. But here is, and I will start with an example. So 5.3. solutions of some recurrence relations. So suppose, we will consider first recurrence relations of the second order, or sometimes called quadratic recurrence relations. So consider the relation of the following type. an plus 1 equals, let me use the same letters. No, an, that's how it is in the notes, an equals a times an minus 1 plus b times an minus 2. Where a and b are constants. So what are we going to do? In the similar way with what we do in differential equations course, we'll try some solution. Let us try. An in the form of geometric series, r to the n. And you can say immediately, but why would we do that? We can say the following, if it works, we'll be awarded for our guess. If it doesn't, it's our own waste of time. So will it work for some r's? Would those sequences work? And so what do? I just plug it in, so I get the following. R to the n equals a times r to the n minus 1 plus b times r to the n minus 2. Then I cancel by r to the n minus 2. Of course, if r is different from 0, then what happens? I'll get the following what? I get r squared equals a times r plus b. So what then? I get a quadratic equation that's called characteristic equation. ar squared minus ar minus b equals to 0. And then if this equation has two real solutions, and that's the only, we'll just analyze the real cases. So two real solutions. Let me call them alpha and beta, doesn't matter. R equals alpha and R equals beta. Or one double real solution. So what happens if we get two real solutions? Then what? We have one solution. So what is the solution in the assumption? An is alpha to the n. Do you agree? Is a solution because that's by our design. Is there another solution? Yes or no? What is it? Bn equals beta to the n. Yes. Let me call it differently because it's not the same sequence. I can call it, B. How would you call it? Can I call it IAN again?
Yeah.
Oh, okay. Yes, I wanted to emphasize that they are not the same. Maybe we can say here xn minus 1 or something like that. Or let me call it an bar. An bar is better. Okay, now it obviously connects with the same equation. So that's it. We have two solutions, but it's very easy to show the same way as we do in these, that if you do any linear combination of those two, you will also get a solution. So how does it look? Actually, we have something called general solution. and it looks like this. AN equals, take any number times alpha to the n, and take any other number times beta to the n. All of them will be solutions. And that's the crucial fact of this section. So this is the methodology to solve recurrence relations of the second order. And then what happens when we have one double solution? I'll postpone that for a minute and show one example. But what I didn't comment, but the example will show that. So among those solutions, which one do we choose? That depends on your initial conditions. So here is full-size problem. Problem 532. Find the sequence satisfying the recurrence relations a n equals 3an minus 1 plus 10an minus 2, and initial conditions what are initial conditions? A0 equals 10 and A1 equals to 1. So what are we going to do? We want to find that the general solution, and how did we say we'll find it? You don't need to write all this. You can immediately remember that there is a quadratic equation that's being formed. So what is quadratic equation? So we are looking at an equals what? R to the n. And then all this after cancellation and everything will give us what? R squared equals 3R plus 10. Is everybody okay with this? So you directly inherit the structure of the recurrence. The highest member gets a square. Next one gets just R. The youngest one gets no R's. What's interesting, you can do this not only for a recurrence relation of second order. It could be third, fourth, any order, as long as your coefficients are constant. The same way as in these, you all have equations of higher order with constant coefficients, linear ones. Now what do? We solve this quadratic equation. R squared minus 3R minus 10 equals to 0. R minus 5 times R plus 2 equals 0. So we get two solutions. So what is that telling you? I have two solutions and I have the whole general solution. So what is general solution? An equals what? I take 5 to the n. I take negative 2 to the n times c and times d. So take each of them. If you take c1 and d0, you get 5 to the n. If you switch and take this 0 and this 1, you get minus 2 to the n, or any combination of those. So how do we determine c and d? According to what? Initial conditions. So when n equals 0, what do we get? A0 is given as what? 10 equals c times 5 to the 0 plus d times negative 2 to the 0. For A1, we get 1 equals c times 5 plus d times negative 2. Yes. So now we solve this system of equations. So 10 is c plus d, and 1 is 5c minus 2d. And then probably we'll eliminate d easily, multiply top 1 by 2, so you get 21 equals 7 c's, so c is 3. And then d is 7. 15 minus 14, yes. So here's our solution. Oops, maybe I shouldn't have done this. Yeah. Doesn't matter, we'll do the repeating case. So our solution is what? AN equals 3 times 5 to the n and plus 7 times negative 2 to the n. And here is explicit formula. Now you don't have to go step by step. If you want 20th member straight there, you can plug it in. So that's how you solve recurrence equations, recurrence relations of second order. Yes? I multiply this by 2 and add it down. So 2 times 10 is 20 and 1 is 21. 2 times c is 2c and 5c is 7c. 2d minus 2d cancels out. Yes?
If we were to use a calculation, just let an equal r at the end.
No, an is r squared. Not r. Oh, you mean I did in derivation, but here, because of that cancellation, when you write characteristic equation, you just write r squared. But if you want r to the end, that's fine.
R squared here because then it goes 2 terms back. So that
Yes, exactly. And a good question is also, how did we know to guess r to the n? That's the same question that you ask as in DE, because you see that power function has that type of behavior. Why? Because look at this. If you have 7 to the n, when you take higher power, what do you get? 7 to the n plus 1. So it increases constant number of times. So people saw that, trying to play with it, saw regularity, and then made a system out of this. The same way as the exponential behaves in DE is that way, because people know properties of the derivative to just stay the same, just multiply by a constant. The same thing here. So that was the idea. Is everybody okay with this?
How did we go from the original to the quadratic form?
So here it is. You look at the ranks. This is rank n. Is that the highest rank? This is next below, and this is 2 levels below. The one that's the lowest just gets a number, so just 10. This one that's 1 below gets r, so you get 3r, and here you just get always pure r squared. That's it. Because that's how you memorize it. Or plug in r to the n as I did the cancellation, but this is easier, yes.
So if it's of a higher rank, like if there's another one,
Then it will be a cube on the left, and then yes, exactly. So it's very easy. All right, what can we do here? This gives us a chance to have a formula for Fibonacci sequence. And let's do it. It's a little bit calculationally unpleasant, but doesn't matter. I think since it's so famous, it's worth going through that little calculation, and shows you also connect a little bit with what we did last time. So I think I had an example like that. Yes, example 533. We want to solve the following one. AK equals AK minus 1 plus AK minus 2. Initial conditions are A0 is 1 and A1 is 1. Do you think that we can do this using this machinery that we just mentioned, yes or no? So what is it? We'll put here r squared, we'll put here r, and we'll put here 1. Agree? Yes.
When you did your example of how this kind of works initially before the problem over there, you said that there was also the possibility
will show you that case.
Okay.
So let's first do two different cases, and then we'll do this one, don't worry. So r squared is r plus 1. And then a quadratic equation. Let's hope it has real solutions. So it does r equals 1 plus or minus root 5 over 2. I didn't say pleasant, I just had real. And these are real unpleasant. And what's say? Exactly. Golden ratio, and it's reciprocal with a minus. Yes. So here it is. Since we are going to do, and basically nothing else, just we need to solve a system, here is a way maybe to kind of save a little bit on that messy calculation, to do it a little safer. So I'll say the following. 1 plus root 5 over 2, I will call it alpha. And 1 minus root 5 over 2, I will call it beta. Because instead of carrying them, I'd better carry alpha and beta. So what is the general solution? The general solution? What? An equals c times alpha to the n plus d times beta to the n. Do you agree with me? Is this what we said? Find two solutions, raise them to n, and mix them up in a linear combination. And who's going to determine C and D? Initial conditions. So when I put A0 equals 1, I'll get 1 equals C plus D. And then what? 1 is also equals C alpha plus D beta. Oops. Do you agree with me? So what? So now, what can we do? Let's eliminate D, for example, or we can do substitution maybe, whatever you prefer. I would probably do elimination. So let me multiply top 1 by beta and subtract. So beta minus 1 is beta minus 1. And then d beta minus d beta cancels out, so I'll get c beta minus c alpha. So from here, I'll get beta minus 1 over beta minus alpha equals to c. All right, how do I get the D? Probably the same way. I multiply first 1 by alpha.
Did you just plug it into the first?
Yes, but then I need to deal with fractions and everything. I would rather work without it. It's absolutely legitimate what you suggested. But I would rather work without fractions and just divide at the end. So I multiply this one by alpha. And C's disappear, so I'll get what? Alpha minus 1, but what? Not beta minus alpha, but what? Alpha minus beta equals 2D. Am I correct about that? So I multiply by alpha, so these cancel. Alpha minus beta, alpha minus 1, that's it. All right. Doesn't look too pleasant. So, so let me see what these guys are. What is beta minus 1, basically? Or what do you, no, what is beta minus alpha, by the way, first? When you subtract beta minus alpha, 1 and 1 cancel. And you get negative root 5 over 2 minus root 5 over 2. You just get minus root 5. Do you agree? And what else? Here is an interesting thing. I can do it with little algebra, but also, you know, there are some famous theorems about quadratic equations, and they are that sum of the zeros is opposite of this number and product is this. So alpha plus beta must be 1, and alpha beta is negative 1. You know, and you can see that. When you add alpha and beta, root 5 cancel and you get 1. If you multiply, you get difference of squares and you get negative 1. So why did I tell you this? Because what is beta minus 1 then from here? Beta minus 1 is actually negative alpha. So this is actually negative alpha over negative root 5, or it is just alpha over root 5. The same way, D is what? Alpha minus 1 is negative beta, and alpha minus beta is just root 5. Just a little unpleasant algebra. So now I can get into the equation and get the following. So how much is AN? How much is C? I'm not going to write it in this form. I will write it in this form. So it's alpha over root 5 times alpha to the n minus beta over root 5 beta to the n. So how does it look? It's what? I can pull out 1 over root 5, and I get alpha to the n plus 1 minus beta to the n plus 1. Well, let's recall alpha and beta. Alpha is 1 plus root 5 over 2, and beta is 1 minus root 5 over 2. Let me check my calculation. Yeah, good. So what is this? This looks very strange. Let me write alpha and beta in their full force. So 1 over root 5, 1 plus root 5 to the n plus 1, 1 plus root 5 over 2, minus 1 minus root 5 over 2 times n plus 1. So it's really surprising because what? Are these numbers integers or they are not integers? We know, no, they are. Fibonacci numbers are integers. And we are writing them in such a strange way with some strange radicals. But what happens? They cancel each other out, and somehow, if you want me to check how much is this when n is 5, put it in calculator and you will get, you know, a Fibonacci number at 5. Yes?
Oh, wait, just.
Yeah, so generally, you know, those root 5 parts cancel each other out, and you get very nice integer. But what else can you see from here? What about this number, 1 minus root 5 over 2? What can you tell me about that number? Is it big? Is it small? Is it positive? Is it negative? First, is it negative or positive? Negative. What's absolute value of 1 minus root 5 over 2? Is it less than 1 or more than 1? This is 2.2 or something. 1 minus, this is approximately 0.6. Is it less than 1? So what happens? When n goes to infinity, since this is base less than 1, that disappears. So this guy disappears. So who is the only one that stays? And that's exactly your goal. Didn't we say last time that when you take a ratio of two members, here is their ratio. Every time you basically do, so ratio an plus 1 over an approximately is golden ratio. this guy disappears, but what else is this guy doing? Since it's negative, when you put it on even power, becomes positive and negative. And that's why it goes, remember last time, up and down, up and down? That's exactly, this second one illustrates that because of that alternation, negative to even and odd powers. So when you are to even power, you are really subtracting, so you go down. On odd power, you are actually adding and you go up. But it gets smaller and smaller, and that's why when you have golden ratio, these members look like this. As we saw last time without having a formula, but now we also have a formula. Is everybody okay with this? So generally, we have explicit formula. Probably we're more comfortable with the previous one, but it's interesting that we also have that explicit formula for Fibonacci sequence. All right, that's another benefit of knowing this mechanism here today. And then let's analyze that other case when you have double solution.
I have a question.
Go ahead.
How do we, in the general solution, just for all these type of problems, how are we building that part back up?
Yes, so exactly like I wrote it here. So you get two numbers, alpha and beta. You make their powers, and then some C and D that are to be determined from IVP. So this is the setup.
Okay.
C times alpha is the number that you already have, beta is the number that you already have. C and D are to be determined from IVP, yes.
For the general solution, how do you get the two equations? Is one of them A1? The two equations are
These two?
Yeah, those two.
Oh, here you plug n equals 0, and then you plug n equals 1. So when you plug n equals 0, I read a 0, and alpha to the 0 is 1, beta to the 0 is 1, so I just get C plus D. On the next one, I have alpha and beta, and I read A1, and then I solve the system. Everybody okay with this? Good. Let's now consider the case when we have double solution. So suppose that characteristic equation has a double solution R. Let's say R equals alpha. What happens then? What happens then? A characteristic equation is that quadratic equation. Quadratic. But I need here some numbers. What were they? A and B or B and C? What were they a minute ago? What are the letters we used here? C. No. A and B. So what happens? So in both problems that we just did, we have two real solutions. If they are two different numbers, and theory says they are linearly independent, they generate everything's super. But what if you get only one solution? Then here's what you do. Solution, if R equals alpha, then general solution looks like this. An equals C times alpha to the n plus D times D, people, what would it be here? When you have double solution, what do you get? Your variable, whoever your variable, you do it x times e to the x. Here it will be what? N times alpha to the n. The same as in these. If you have double solution, you have x e to the rx. Remember that? And here is n times alpha to the n. And that's it. Solved and everything. What's the only question that's missing here, or only information that's missing here? Why? Why would this guy be solution? So let's see. So why is this n alpha to the n? So why is n alpha to the n also a solution? Here's the reason. How do these equations with a double solution look like? Do you think that this quadratic equation has a double solution? Or it doesn't have a double solution? Why not? Does this one have double solution?
Yes.
So generally what? Those that have double solutions are basically what? Perfect squares, because that's what you have. Because when you have perfect square, you say r minus 3 times r minus 3. So both your factors are r minus 3. So who's your double solution? 3. R equals 3. Agree? So so when you have equation like this, then actually double solution means that your equation looks like this: r squared equals r plus b has the form r minus alpha squared equals to 0. When you get it to the left, you can complete the square. So that means that r squared minus ar minus b is the same as r squared minus 2r alpha plus alpha squared. Because if you complete a square. So from here, if that happens, then what? Minus a must be minus 2 alpha, so a must be 2 alpha, and b must be negative alpha squared. So that happens only, as I said, when a is 2 alpha and b is negative alpha squared. Like here, if it's 3, 3, then b is twice that 3 with a negative, and then b is alpha squared. Then what? Let me plug in now. Plug or try an equals n alpha to the n. What do I get? The left side looks like this. N alpha to the n, and I'm asking, is it equal? I'm checking this. Is equals a times n minus 1 alpha to n minus 1 plus b n minus 2 alpha to the n minus 2. I plugged in my n alpha to the n that I claim is a solution, and I want to see if that's really true. For this to be true, what can I cancel by? Can I cancel by something? So this is equivalent, so I'll keep question mark. They are equivalent equations, they are both true or both false. I'll have n alpha squared. I'm asking, is it equal to a times n minus 1 alpha plus b times n minus 2. But now I will replace what a and b are in terms of alpha squared, and I'll get another equivalent equation. So what would that be? It is equivalent to the following. I hope I'll finish it here. Is n alpha squared equal? I'm asking if it will be satisfied. I'll keep my question mark. A is 2 alpha, so it's 2 alpha n minus 1 alpha minus alpha squared times n minus 2. And let me, is this true? I don't know yet, but it's true, it's equivalent. In this course we know what does it mean when statements are equivalent. What would that be if I did alpha times alpha is alpha squared, so I'll get 2 alpha squared and minus 2 alpha squared minus alpha squared and plus 2 alpha squared. Is it true or not? I don't know yet. I'll cancel 2 alpha squared. Now it's clear that this is true. Why? Because how much is 2 alpha squared n minus alpha squared n? Alpha squared n on the right, alpha squared n on the left. So this one is true. And then all the others being equivalent to a true statement are true. So really n alpha to the n is the solution. And then what? Here I'll say something that we don't have time to discuss fully, but you maybe heard in some other courses. Those two solutions are linearly independent. That's why they build all the other solutions, and that's why this will make all of them. So here is the way to set it up. So this is the one that